Hi. We're going to find the locations of characters in a given text where those characters are followed by an identical character immediately to their right. We don't want the characters themselves, we don't want the indices, we want a mask that indicates where such pairs begin. Classic example for text processing things in APL is using Mississippi because it's got a lot of duplicated characters and identical characters spread out. But it only ever has two identical characters in a row, so let's add a little bit more where we have three in a row and we'll have overlapping pairs. What we want to get here is these are not the same, that's a 0, these are not the same, that's a 0, these are the same, that's a 1, and so on. At the very end, we want that these two are not the same, that's a 0, these two are the same, 1, these two are the same, that's a 1, and then this character is not followed by an identical one because there are no more characters there, so we always end with a 0. Let's start with a lambda, and we can refer to the function's argument with omega. It's because the argument is on the right and it's the rightmost character of the Greek alphabet. And we always have the whole solution right out of the box with an n-wise reduce. This means we go over all the windows of length 2 in this case and reduce them using equality, which effectively just inserts the equality between the two elements, the two characters. And that gives us this, which is almost correct. The only thing we're missing is because there is no pair of the last character with one more character after it, there's no 0 at the end. Now, we might think that, oh, that's easy to fix. We can just stick a 0 on the end and solve the problem. However, if the argument is empty, so just an empty string, let's apply this lambda on each one of these, then we get a length error on the n-wise reduction because it cannot find any pairs of length 2. So how might we solve this instead? If we extend the argument with a character that doesn't appear anywhere, then we can solve the problem. And we see that the empty string indeed gave us an empty result. However, this is of course problematic. If the string ends with a plus, we get the wrong result. We can never get a 1 at the end because that last character, even though it's a plus here, is not followed by a character that's identical to it. So we need to solve this problem. And there are a couple of ways that we could do so. Here's a little bit of a clever one. Let's take the reverse of the argument. This gives us all the reverses. And then we take the first one, which you can actually see by the color here is optimized. So we're not actually reversing and taking the first. We directly take the last one. It's just a way of expressing it. So here we get a 1, and notice that we get a space here. And that is because the first coerces out an element when there aren't any elements. And it takes a prototypical one, which for text is a space. And then the plus for here. So this is the last element, or a space if there aren't any. And then we can take some filler characters that we can add to the string to compare it, just like we did with plus before. But we need a couple of different ones, because if the last one is a plus, we want a different character. And then we can use a set difference. So this takes this set of plus and minus and removes all the instances of the last character. So for the first one, we remove all the i's, then we remove, there aren't any, so it doesn't, sorry, not all the i's, the ones, there aren't any, so that doesn't matter. Then remove all the spaces, there also aren't any, and then remove all the pluses, and that gives us just the minus left. And then we can select the first one of that. And this gives us a filler character that we can safely use. The last character cannot be both plus and minus at the same time. In fact, we don't actually need plus and minus here, because just like we used first before, and it coerced out an element when there weren't any using the fill, if we just use plus by itself, then we can see here we get plus when plus is not the last character, and we get nothing when plus is the last character. And if we do first on that, then we get a space at the end, and space is not equal to the last character, so it's a safe character use, even though it's hard to see. Okay, so now we can take the argument and concatenate it with this safe filler character, and we can do the two-wise reduction and get a correct result. So this is one way to solve the problem. Let's start over for a moment and try something else. Again, we'll do the n-wise reduction, but we know we want a 0 at the end. Let's add a 0 at the end, so this is concatenation with swapped arguments, and therefore we put it at the end. We saw before that if you try to do this on an empty argument, then that's not going to work. We get an error there. So if we run the n-wise reduction here on something with just one more character, then we get, oh sorry, we need to make it into a vector. Then we get an empty result, and that would be appropriate result for the empty case. So really all we need to do is, if it's empty, we need to add one more element. And how can we do that? Well, we can take the length of the argument, and let's go back to the case that we had before. So here we have the length of the argument, and we don't want it to be 0. We want it to be at the least 1. So we can clamp it using the max function. So this is the maximum of 1 and 17 and the maximum of 1 and 0, and that gives us this length. Then we can use this to take, and we need to take from the other side. So normally we take the length on the left and the data on the right, but we want it opposite, so we swap it around with the commute operator from the argument itself. And now we can see that we've added a space only in the case where we have an empty. Okay, now it is safe to do the n-wise reduction. And this gave us the correct result for the empty case, but we're still missing the 0 over here. What we can do then is we know how many elements we want, namely the length itself. So we can take the length again of the argument and take with that. And if take doesn't have enough elements, it will pad with the appropriate prototype. And that would be a 0 in a numeric case that we have here. So this gives us a correct result for both of them. Now we can, this function happens to turn out really nice if you convert it to a tacit form, which means that we don't mention the arguments explicitly. Rather, all arguments, or the only argument here, is referred to in terms of function application on that argument. So it's pretty easy to see here that what we're actually using is, should we say, an aspect of the argument, which is its length. Let's parenthesize this just for clarity. So we're referring to the argument in terms of its length. Over here, we're also referring to the argument in terms of its length. Here, we're not referring to it in terms of any function directly applied to it. But that would be the same thing as an identity function applied to it. And luckily, we do have an identity function. It looks like this. It points at the argument. So now that we have crystalled out, so to say, indicated what our referring to the argument looks like in terms of function application, we can then go ahead and remove both the braces that indicates this explicit lambda, or defen as we call it, and the actual name of the argument, Instead, we're going to replace it with round parentheses. And so here we get rid of the names. And this works. We don't actually need these parentheses around functions. We can just use the functions directly. This is a very nice and clean looking train or tested function for solving the problem. Thank you for watching.